Good day. With your permission, I present a work, Modified Neural Network Method for Stabilizing Multi-Rotor Unmanned Aerial Vehicles. Over the past years, the topic of studying unmanned aerial vehicles is becoming increasingly widespread. Of particular interest, the multi-engine type unmanned aerial vehicles. Unmanned aerial vehicles with remote control driven by several air screws located in the same plane. Nevertheless, there are a number of technological barriers that restrain the pace of development of the unmanned aerial vehicles industry. Among scientific works, there are a number of articles describing by the dynamics and management of a quadrocopter with a modernized design. In this work, the problem of optimal control of multi-core unmanned aerial vehicles is solved, in the solution of which there of that version of the proportionally integral radio regulator, PID regulator, is almost always applied. It should be noted that the use of standard positioning sensors, accelerometer, gyroscope, requires special studies due to the fact that the accumulated measurement error can significantly distort the output information. Therefore, most of all existing publications are devoted to the appropriate algorithm for construct departments and comparing their effectiveness, including use these sensors. The use of a neural network controller will make it possible to quickly adapt to external influences, which is important for achieving optimal unmanned aerial vehicles flight in real conditions. The unmanned aerial vehicles control system with the properties necessary for use in a more complex order control systems can be intellectual control system, construct, or a hybrid control neural controller. This figure shows an unmanned aerial vehicles hybrid neural network control diagram, which was developed by this authors group. Training through the identifier is necessary not to interfere with the normal functioning of the object by trial action used for training. In addition, such a diagram allows you to implement predicate control and increases the safety of the unmanned aerial vehicles. We assume that as a neural network, in the general case, a dynamic, recurrent neural network based on the perceptron, recurrent multilayer perceptron, RMLP, the structure of which is shown in figure. The neural control diagram with an emulator and controller is developed by this authors group and presented in figure, where a neural controller trained on the inverse model of the control object and the neural emulator of the real model of the control object. There is unmanned aerial vehicles. The neural controller trained method based on a neural emulator using the method of reverse distribution of the error is described. For training a neural emulator that is based on the RMLP neural network, a gradient training algorithm is used. It is worth noting that the gradient training algorithm for a recurrent multilayer perceptron RMLP is systematized by Stanislav Osowski in the book Neural Network for Information Processing. As in the situation with a unidirectional network, a gradient of the target function relative to each weight is calculated. As the initial data for training and test samples, the diagram of quadrocopter roll angle fluctuation is taken. Table contains a fragment of the training sample of the values of the quadrocopter roll angle fluctuation. The complete training sample contains 265 rows corresponding to different test modes. This slide shows the neural network training results. You can see, given signals of a dynamic objects, unmanned aerial vehicles, RMLP network training diagram with a single adaptation of the weight in each circle for a dynamic object, unmanned aerial vehicles, from the first experiment. RMLP network training diagram with 3 times adaptation of weight in each circle for a dynamic object, unmanned aerial vehicles, from the first experiment. Specific signal of a dynamic objects, unmanned aerial vehicles. RMLP network training diagram with a single adaptation of the weight in each circle. RMLP network training diagram with 3 times adaptation of weight in each circle for a dynamic object, unmanned aerial vehicles, from the second experiment. The problem of stabilization in angle is considered and stabilization in height is not taken into account. The pitch controller used error data in the vehicle's pitch angles, roll, pitch, and yaw, the dynamics of these angles, and the accumulated error. The modified neural network training algorithm you can see in this slide. Upper figure shows the stage or calibration of the coefficients by the network after a different number of iterations for the roll angles of the quadrocopter. A stand with 1 degree of freedom was used as a stabilization object on which a quadrocopter is installed with an initial roll deviation of 10 degrees. Bottom figure shows the behavior of the unmanned aerial vehicles when adding random perturbations, which are small random change in the angle at each stabilization step. It can be seen that adding even small additional impacts on the angle increases the time required to stabilize the model. It takes at least 1,000 training iterations to bring the model to a stable state. This figure shows the comparative analysis results. The conclusions are presented on this slide. Thanks for attention.